Welcome back, students. In this video, we're going to look at hydroboration oxidation, but of alkynes this time. Remember when we looked at alkenes, hydroboration oxidation put the OH at the less substituted position. That's going to happen as well with alkynes, but we're only going to see a reaction with one of the pi bonds. When we see one pi bond react, the other one sticks around. So let's go ahead and draw our 3 carbons here. I'm going to keep one of my pi bonds. And then because the OH adds to the less substituted side, I'm going to find the less substituted side of my pi bond and put an OH there. So this is what my product would be. I say product in quotations is because this is not my final product. This is something called an enol. An enol has an alkene and an alcohol. And the enol, the alkene and the alcohol have to be connected to one another, right? So enol is alkene plus alcohol, where the alcohol has to be attached to one of the carbons that's involved in the alkene. What happens to these? Well, they do something called tautomerization. Enols rapidly tautomerize. You cannot isolate an enol very well at all. And they tautomerize with even the smallest amount of acid or base. Well, during the reaction, you added a base. You don't believe me? Let's go back. Look at this second step, right? You added sodium hydroxide right there. So you definitely have base in order for this reaction to happen. Let's look at how our compound from the prior page is going to tautomerize in the presence of base. We're only going to focus on the Basecatalyzation here because that's what's applicable. In an earlier video, we went through the acid catalyzation. So let's start. The first thing that happens is your base pulls off the proton and the electrons go onto the oxygen. When that occurs, now we have an oxygen with a negative formal charge. I want to draw a resonance form for this. We're going to take a pair of electrons, swing it over here, and then this pair of electrons is going to end up becoming a carbanion. Now we have a C double bond O, and we have a lone pair here. At this point, we have made water, right, because our hydroxide came in and pulled off a proton. What we need is to make hydroxide. Because this is a base catalyzed process, we need to end up with base at the end. In order for us to do that, something has to pull off a proton from water. And you know what's going to do it is this here. It's going to come around, pull off that proton, do a proton transfer so that you get your final product and you've recreated your hydroxide catalyst. Notice how our final product here, just like in our earlier video, has a C double bond O. The difference is this one's an aldehyde. I'm going to draw in that aldehydic hydrogen there because it makes it look a little bit more normal. Let's look at the overall reaction. What you're going to see here is that I've actually changed reagents. And I'm going to talk about that on the next page of what the acceptable reagents are. But for right now, let's talk about how we're going to predict the product. Yes, you could draw the enol and then you could draw the tautomerization, but we want to be faster than that. We want to start to see patterns. I mean, you should be able to draw the enol and the tautomerization, but again, we still want to be faster. What I need you to do is look for your triple bond in your molecule. Once you find your triple bond, go ahead and find the less substituted side. That less substituted side is where your C double bond O is going to be. So we can go ahead and draw our 3 carbons and at the less substituted side put on our C double bond O. If it makes you feel more comfortable to draw the aldehydic hydrogen in, that's just the hydrogen that, makes this look like an aldehyde that it is, go for it. If you don't want to draw it in, that's fine too. Both are fine. So that's what you're going to do. You're not going to draw the enol. The enol is not your final product. Even if we change the reagents, see how you still have base there? That base is going to be present to tautomerize your enol into an aldehyde. For the second one, again, I want you to find your carbons that are involved in the triple bond. Find your less substituted one. that carbon is where you're going to have the C double bond O. So draw the rest of your carbon structure, and then the less substituted side is your C double bond O. What if you have an internal alkyne? What if you don't have a less substituted side? Well, you need to be looking at this for the possibility of two different products, because you could add to that side or you could add to this side. Let's draw both and see what happens. So if I add a C double bond O to the left-hand side, then I get this as a product. If I add my C double bond O to the right-hand side, I get this as a product. Those are the same, so you would only draw one. But if the carbon structure changed, pretend I had, something like this, then you would absolutely have two different products. Now let's talk about the reagents. The reason that we changed reagents away from the one that we saw earlier, the BH3-THF, right? BH3 complexed with THF, was because BH3 and THF are reactive enough, that borane is reactive enough to react with both pi bonds of your alkyne. So what we do is we change the BH3 a little bit, take off two of the hydrogens and put two R groups on to make it less reactive. And that way, we're only going to see a reaction with one of the pi bonds. So there are three ways to draw this dialkyl borane compound that is less reactive than regular borane. One way is the very general way, to just put in an R here for the fact that you are illustrating that you have a boron and one hydrogen and then two alkyl groups. The second and the third options that I've listed here and here are also dialkyl boranes. They're just specific molecules. This first one is when you have a boron with a hydrogen and then some carbon groups attached to it. Like this. And then the other one, the 9BBN, is a bicyclic structure where, again, the boron is within the bicyclic structure, so it has two alkyl groups on it. So you could use any of these to perform the hydroboration oxidation reaction of alkynes. Let's wrap up. In this video, we looked at hydroboration oxidation, but this time of alkynes. We are still seeing an H and an OH add across the pi bond, and we are forcing the OH and OH to add only once across one pi bond by changing up the reagents. We form the enol, and the enol, again, tautomerizes really rapidly into, in this case, an aldehyde. Remember that the OH is adding to the less substituted side in this reaction, which is why you get an aldehyde instead of, when we looked at the last reaction in our last video, you get the ketone. Thanks so much for watching. This is Ketone signing out.